Okay, so what I'm going to do now is walk you through a little bit about complex roots of unity. It's good to have a bit of a think about what we're actually doing here. And because if you understand what you're doing, you probably have a far better chance of getting the right answer. Let's have a bit of a think about this. Like z is a complex number. Now, if I plot that, z equals 1, it's just here. And that's easy. Let's say we get z squared equals 1. Now, you've solved this before. Now, whether it's a complex number or a real number, if I said z squared equals 1, that means z equals plus or minus 1. So, because if you find the square root of both sides, you get plus or minus square root of 1, so you get that. So, we've got an answer here, we've got an answer here. So, because that's a power of 2, we've got two answers. If I ask you to find z cubed equals 1, you're probably thinking of z equals 1, because 1 cubed is 1. Minus 1 cubed is minus 1, so minus 1 isn't a possible answer. But the difference between what we've got in the real plane and the imaginary plane is this. Well, we had two answers here, but this we're going to go back to one answer. There are actually two other answers as well, because we've got a power of 3. We should probably get 3 solutions. What I want you to think about is, if that's one of the answers, this is what's called the unit circle. So every complex number on here has a modulus of 1. Okay, that one there, they're all got a distance of 1 unit away from the origin. What's another complex number that I can put on this unit circle such that when I raise it to the power of 3, it's going to end up back at 1? Well, clearly 1 cubed is 1, and that makes a little bit of sense. But there's other complex numbers here where I can plot, which would come back when I multiply them to, or raise them to the power of 3, end up back at 1 as well. I'll pause it now and have a bit of a think about where you think that would be, and then I'll show you where they are. So pause it now. Okay, so this is where they are. I'm going to draw another one over here, and I'll show you why, this one works. I'm going to make that angle there 120 degrees. Now 120 degrees is 2 pi on 3. So if I had a complex number which had a modulus of 1 and a argument of 2 pi on 3, I could write that as cis 2 pi on 3. Now, if I raise that to the power of 3, remember with the modulus you raise that to the power, but you multiply the argument by that number, so you get cis 2 times pi, or 2 pi times 3 is 6 pi on 3, which is cis 2 pi. Now, 2 pi is 1 rotation, so it comes back to here. So that complex number here is actually a solution to that as well. So we call this cis 2 pi on 3. Now there's another one as well, such that when you multiply the argument by itself 3 times, it ends up back on here. And it's down here. There's another reason about thinking about this. First I'm going to call this 240 degrees. Now 240 is 4 lots of 60. Yeah, so that's cis 4 pi on 3. Now I'm going to raise that to the power of 3 just to test that when I cube this number I end up back on 1. So that gives you cis 12 pi on 3, which is cis 4 pi. Now 4 pi is just a multiple of 2 pi. So 0, there's 2 pi, there's 4 pi, it comes back to here. We don't tend to write it as cis 4 pi on 3 because the argument is generally written between 180 and minus 180. So you actually need to write that as cis minus 2 pi on 3. Now we can actually write that as z equals 1 or cis plus or minus 2 pi on 3 perhaps, but I tend to split them up like that. The other thing that we know why this is a possible solution, this one and this one here, is if you've got a complex number which is a root of a polynomial, its conjugate is also a root. So that's the complex conjugates theorem as well. So anytime you've got a complex number that's a solution, its conjugate will be 1 as well. Have a bit of a think about z to the power of 4 equals 1. Now we know that 1 to the power of 4 is 1. We also know minus 1 to the power of 4 is 1. So I'm going to get answers here and here. But where else do we have answers? Because I'm probably expecting 4. So z equals plus or minus 1. There are some other ones as well. It's going to be this one here and this one down here. This one here has an argument of 90 degrees. So it's cis pi on 2. Now if I raise that to the power of 4, I get cis 4 pi on 2, which is cis 2 pi. Now that's right back here. So that means that that number raised to the power of 4 comes straight back to that 1. So cis pi on 2 is an answer. I can call this cis 3 pi on 2 as well, and I can multiply it by 4. So when you raise an argument to the power of 4, or something in mod arg form to the power of 4, you multiply the args together. But also, because that's a complex number, remember that's I, this one here is minus I. So you can probably write that one there as I, and the other one is minus I, so it's not right, this is plus or minus I. A couple of things that you'll notice is, one, these numbers here, these 4 are evenly spaced out. 4 complex numbers evenly spaced out around the unit circle. Have a bit of a think about this. Z to the power of 5 equals 1. What are the 5 possible numbers that I can substitute in here such that when I raise it to the power of 5 is equal to 1? Well, clearly one of them is going to be 1, because 1 to the power of 5 is 1. But I need 4 others. Now, they're going to be equally spaced out around this unit circle, and I'm going to get 4 others. Now, they're going to be in conjugate pairs. Okay, so we need 5 roots equally spaced out around it. So let's have a bit of a think about a complex number that I could put here that when I raise it to the power of 5, it will end up back at this point here, because that's really our goal. So if I've got 2 pi, which is all the way around, if I divide it by 5, it will give me that one, that one, that one, and that one. Now this is 2 pi and 5. This angle here is 4 pi and 5. This angle here is 6 pi and 5. This angle here is 8 pi and 5. So really what I've done is I've split up 2 pi into 5 equal lots, where each angle is a difference of 2 pi and 5. Got a solution here, solution here, solution here, solution here. Now notice complex conjugates. Again, these are conjugates of each other. The imaginary part changes. Let's just test this first one. Like, this is really cis 2 pi and 5. So cis 2 pi and 5 raised to the power of 5. Remember, I don't have to worry about the modulus, because modulus is just 1. That's why we do it on the unit circle. Well, they always are, invariably. I'll show you when they're not. And if we multiply 2 pi on 5 by 5, we get cis 10 pi and 5. Now that simplifies to cis 2 pi. And where's 2 pi? 2 pi is, boom, it's there. So that works. The same works with 4 pi and 5, 6 pi and 5, 8 pi and 5. 8 pi and 5 times 5 is 40 pi and 5, which is 8 pi, which is 4 lots of 2 pi. It just keeps going around and around and around. So what we end up with this. These are our answers. Cis 2 pi and 5. Cis 4 pi and 5. Cis 6 pi and 5 and 8 pi and 5, which actually generally write going this way. Now if that's 6 pi and 5, this one's minus 4 pi and 5. So we write cis minus 4 pi and 5, cis minus 2 pi and 5. There's our complex conjugates matching up there and there. And we've got 1, 2, 3, 4, 5 solutions. So that's what we're going to do, and we're going to apply some pretty easy de Moivre's theorem stuff to do that now. So I'll do an example for you now.